Natural gas, also called fossil fuels, supplies approximately 25% of the world's total commercially traded primary energy requirements. Natural gas is a mixture of paraffin hydrocarbons, which have the general formula CnH2n plus 2. Natural gas is abundant, versatile, and generates less air pollutants than other energy sources, namely very little amounts of NOx, CO2, and negligible amounts of SO2. All of these factors are drivers for the steady growth of demand and consumption of natural gas. However, in its gaseous state, it has a very high volume and poses difficulty in transportation over long distances. This is why liquefied natural gas is so important. It enables the transport of natural gas internationally and across oceans. The criteria of this project will be qualities that help determine the success of our project. The two most important criteria is lowering capital and operating costs and choosing the most established technology. Cost of capital represents the return the project needs to achieve in order to justify the cost of a capital project, and operating costs are the expenses incurred from day-to-day operations. It's important to reduce these costs in order to increase profitability. In terms of choosing the most established technology, there are many different alternatives to many of the pieces of equipment in this project, so choosing the most established is important. Constraints are hard limits which we cannot cross in order to proceed with our project. These constraints include regulatory requirements, environmental and safety standards, land and resource availability, technological limitations, and market conditions.
This process flow diagram shows the different stages of the liquefied natural gas importation process from the arrival of the LNG carrier to the regasification and delivery of the natural gas to the end users. The PFD shows the different equipment and systems involved, like the unloading arms, storage tanks, pumps, heat exchangers, compressors, and vaporizers. Aspen is a process simulation software, and by the selection of appropriate thermodynamic models and inputs, it could predict the performance of the process. Here we can see our four main Aspen simulations, and we have used those simulations in Aspen to size our equipment by choosing the most extreme condition for each piece of equipment out of all simulations. For example, we would look at the largest flow rate that would go through a pump to size that pump, and from there we also use them for costing and performing mass and energy balances. This is one example of what an Aspen simulation would look like. Here we are trying to find the amount of supplemental heating needed for the vaporizer in winter. So by specifying the appropriate thermodynamic models and inputs and specifying the air temperature of that month and having all pieces of equipment that are needed, we are able to get that.
Individual bare module costs were calculated based on technical specifications of each piece of equipment, such as flow rate, diameter, operating pressure, among others. Then, the individual costs were added up to a total to get the total bare module cost. To calculate the cost of LNG, a price was determined within the range of $2.25 to $3.5 per million BTU. This range is used for long-term contracts with the Algerian LNG exporters. In addition to the LNG used for send-out, extra LNG will be needed to be purchased for supplemental heating. In the ORV plant, seawater needs to be heated during the days where the water temperature is below the requirement. In the Mussing plant, the heating fluid needs to be heated when the air is below specified temperature. The plant requires 1,050 million square foot per day of natural gas send-out. The sales price was set by averaging the Henry Hub natural gas spot price for the last 5 years. From year 0 to 2, both projects experienced negative cash flows due to investments and working capital requirements. From year 3 onwards, both projects generate positive cash flows. In year 9, the cumulative present value turns positive for both projects, indicating that the project has recovered its initial investment and starts generating a net positive value for the investors. The Mustang Intelligent Vaporizer plant has a higher overall CPV, indicating better financial performance.
Here are some specific equipment details listed in the chart below. We start with our storage tank. We outline here our volume, height, diameter, pressure, temperature, and material requirements, and that follows through the rest of the chart with each further piece of equipment, including our pumps, which have a unique row here, which is our capacity factor. This denotes how many of those pumps at that location will be needed. At 50%, we would need 2 pumps. At 10%, we would need 10. Beyond that, our more specific pieces of equipment include our compression suction drum pump, our dock drum, our recondenser, and our vaporizers, as well as some of our heat exchangers. Here are some specific equipment details listed in the chart.